Hey everyone, and welcome to another explainer. Have you ever wondered why the exact same amount of gas can take up completely different amounts of space depending on the room you're standing in? Well, today we're completely cracking the code on molar gas volume. We're going to visualize exactly how gases behave under standard temperature and pressure versus room temperature and pressure. Whether you're prepping to secure every single mark on your next chemistry exam, or, you just want to understand the real-world mechanics of filling a party balloon or inflating a car tire, this explainer is going to map out the physical theory and the exact calculations you'll need.
So here's our game plan for today. First, the expanding gas mystery, followed by the differences between STP and RTP. Then, we'll equip you with the gas volume formula, walk through some step-by-step calculations, dodge those common exam traps, and finally, lock in your ultimate exam strategy.
All right, part 1, the expanding gas mystery. Why gas volumes change. Okay, let's dive into this. It's a question that honestly stumps a whole lot of students at first glance. How can the exact same amount of gas, literally the exact same number of molecules, take up completely different volumes just depending on the outside conditions? I mean, think about a car tire looking kind of flat on a freezing cold winter morning, but then perfectly plump in the sweltering summer heat. What is actually going on there?
Well, to solve this mystery, we need to define our core term. Molar gas volume is the specific volume that one single mole of any gas occupies at a given temperature and pressure. I really want you to pay close attention to those two variables, temperature and pressure. Those are the ultimate levers controlling our gas. If you tweak either of those two, the physical boundaries of the gas change immediately.
Moving right along to Section 2, STP versus RTP explained, standard versus room conditions. And this brilliantly illustrates what happens behind the scenes. On one side, we have STP, standard temperature and pressure, which is defined exactly at 0 degrees Celsius and 1 atmosphere. On the other side is RTP, room temperature and pressure, sitting a lot warmer at 25 degrees Celsius, also at 1 atmosphere. Notice the molecular behavior here. At RTP, the higher temperature means thermal energy is transferred directly to the gas molecules. Watch those directional vectors pushing outward. Because the molecules are bouncing around with much greater velocity at 25 degrees, they exert a stronger force on their invisible boundaries, and that causes the gas to physically expand.
Because of these specific conditions, scientists have calculated some universal constants for us. At STP, 1 mole of any ideal gas occupies exactly 22.4 liters. Burn this massive number into your memory. 0 degrees Celsius, 1 atmosphere, exactly 22.4 liters per mole.
But as we shift to RTP, when we turn the heat up to 25 degrees Celsius, that exact same mole of gas expands to take up 24 liters. It's the exact same amount of physical stuff, right? But those faster-moving molecules just demand more space.
Part 3, the gas volume formula. This is your toolkit for calculations.
So now we need the mathematical toolkit to actually execute our exam answers perfectly. And the formula is beautifully simple. Volume of gas equals the number of moles multiplied by the molar gas volume. Or for the math shorthand, V equals N times Vm. V is your total volume, N is your number of moles, and Vm is that constant we just talked about, which will flip between 22.4 or 24 depending entirely on your conditions.
Which brings us to Section 4, step-by-step gas calculations, executing the math flawlessly.
We are going to treat every single calculation as a strict chronological flowchart. You absolutely must follow the sequence to guarantee full marks. Step 1. Identify your condition straight from the prompt. Is it STP or RTP? Step 2. Apply the correct Vm constant to your formula. And Step 3. Execute the math. Let's run this exact flowchart in real time using 2 moles of oxygen gas.
First up, let's look at 2 moles of oxygen at STP, following our flow. Step 1, we know it's STP. Step 2, our formula dictates a Vm of 22.4 liters per mole. 2 moles multiplied by 22.4 liters per mole mathematically yields a total volume of 44.8 liters. Boom, done.
Now, what's really interesting about this is contrasting it with RTP conditions. Step 1, it's RTP. Step 2, our Vm shifts to 24 liters per mole. So, 2 moles multiplied by 24 liters per mole results in 48 liters. The exact same 2 moles of oxygen take up 3.2 more liters of physical space simply because the room is warmer. How cool is that?
Section 5, dodging common exam traps. Protect your marks.
When you're sitting in that exam hall, the pressure is totally on, and it is so easy to fall into traps. Let's break down the incorrect path versus the correct path. The single biggest misconception students make is assuming gas volume just remains constant. They memorize one number, usually 24, and apply it blindly to literally every question. The correct path? Always checking the prompt for STP or RTP first. The second massive trap is using the incorrect units. Liters are equivalent to cubic decimeters, or dm cubed. If the question hands you a volume in cubic centimeters, cm cubed, you absolutely must convert it to dm cubed before running your calculations, or your final magnitude will be way off.
And finally, Section 6, Final Exam Strategy, Cheat Codes for Full Comprehension.
So the crucial point is to chunk these final takeaways neatly into your mental toolkit. Whenever you face a gas question, number 1, aggressively identify STP or RTP in the text. Number 2, lock in your constants. STP equals 22.4, RTP equals 24. Number 3, always verify your units are in decimeters cubed. And finally, practice this math with different gases, because remember, this molar volume rule applies universally to all ideal gases, whether it's oxygen, nitrogen, helium, you name it.
Before we wrap up, I want to leave you with a provocative thought to really test your new intuition. Knowing exactly how and why gases expand when heated at the molecular level, which condition, STP or RTP, do you think you'd use to accurately calculate the volume of a hot car tire after a long summer drive? Would a standard calculation even work, or would the pressure be completely different? Keep that in mind as you apply these concepts to the real world. Thanks so much for engaging with this explainer. Definitely use these workflows in your study sessions, and good luck on those exams.